Right, so we're going to move on to the final part of our review of calculus and computer science, and this is a subject called integration, which is particularly important with regards to area measurement problems. Right, so let me just review what we've seen in the first part, this subject called differential calculus. In differential calculus, one of the most important applications in computer science is in this area called solving optimization problems. And the way we do that, we analyze what are called the critical points of a function. So a critical point of a function is a value for which the first derivative of that function is zero. This first derivative notion, that is derived as a means of considering the gradients of a line related to points of that function. In other words, it turns out to be a function which is obtained by describing how something behaves as a value approaches a particular limit. In particular, the limit we're interested in is this notion of a value approaching zero. So by limit, we mean something that is allowed to get arbitrarily close to the value zero in this case, but is not allowed to reach that value. So a limit approaches but never reaches. What about integral calculus, a subject we'll be looking at in this lecture? Integral calculus concerns a problem which I have been maintaining is fundamental to computer science, the problem of measurement and counting. So integral calculus is very closely connected to a basic computational problem. It originates in a technique which goes back to classical Greek mathematics called the method of exhaustion, and its principal measurement application is in measuring area of surfaces. The way in which integral calculus is connected to differential calculus is in two connections. Both of them use this notion of limit. Integral calculus uses this notion of what I'll be referring to as the antiderivative of a function. There are some complications. When we look at integral calculus, we'll see that there are very often a number of technical issues that arise which did not arise when we were considering differential calculus. Okay, here's a basic problem as a motivating one. So we have some function. In this case, the function f of x is x squared. We've drawn how that function behaves, this curve here. And what we want to know is the area spanned by that function, by this curve, between two particular points, in this case 6 and 14. So we want to know, in simple terms, what's the area of this blue region here. So, well, there are a couple of simple approximations we can make. Suppose we think of drawing a rectangle whose base is of length 4. And we see how those rectangles, this one and this one, relate to the function we've just drawn. Well, it's not too difficult to see that this length, the dark blue area, it's at least the sum of the areas of the orange rectangles. And we know how to measure their area. Measurement of a rectangle area, we just multiply the lengths of the two sides. So in this case, 4 by whatever this value turns out to be, 4 by whatever this value turns out to be. That's for the orange rectangles. So we know this area, the dark blue area, is at least the sum of the areas of these two rectangles. We also know it's at most the sum of the area covered by these two light blue rectangles. So the area, that area, 4 times whatever this value is, plus 4 times whatever this value is. So we have a very simple, a very crude mechanism for getting a lower bound on the area that we're interested in, and for getting an upper bound on that area. The lower bound, this plus this, the upper bound, this plus this. What if we want to measure the area exactly? Well, before we see how to do that, let's try and get a better approximation. So on the previous slide, I used rectangles whose base had length 4. What if I moved to rectangles whose base had length 2? So this case, and this case. There's one thing we notice. First of all, the total area of the orange rectangles, that's still a lower bound, but it's a better lower bound, okay? So we add up the areas of these 4 rectangles, that is closer to the area that we are trying to measure. The same thing with the light blue rectangles. If we add up those areas, that is still an upper bound on the area we're trying to compute, but it's a better upper bound than the one we had previously. So this total area and this total area, these are closer to each other. So suppose we try and extend that idea of looking at the measurement of rectangles but using better and better approximations. What do we find? Well, the technique I've just been describing, this is what is called the method of exhaustion. As I said at the start, this dates back to classical Greek mathematics, and its idea is to try and approximately solve hard area calculations by using smaller and smaller shapes whose area it's easy to calculate. So objects such as rectangles, objects such as triangles. As we saw in the previous 2 slides, on some occasions, the method of exhaustion is going to come up with too large. It'll overestimate the area that we need. So the light blue rectangles in the previous 2 slides. And sometimes it's going to underestimate the area we need. So the orange rectangles in the previous 2 slides. However, as we choose smaller and smaller shapes to cover the whole area, we'll get better estimates. We'll get better upper bounds, we'll get better lower bounds, and these will become closer. So let's look at a few statements of what I hope are obvious. Suppose we are looking at an area between 2 points, say this point, and we are going to assume that our first point is smaller than our second one. So the first question we can ask is, how many rectangles with a particular length of base, particular base width, can we fit into the space between this point and this point? And it's not too hard to see that that number is, we just subtract the smaller end, this value, from the upper end, this value, and we divide that number by the total base width that we're going to be using. What can we say? Let's suppose we've chosen a value of t. What can we say about the rectangles between t and some point t plus h when we are looking at an arbitrary function f? Well, one thing we can observe is that the area that is covered by that rectangle, it must be some value between h multiplied by the value of the function at t and h multiplied by the value of the function at t plus h. So that gives us a couple of consequences. First of all, it allows us to derive general lower and upper bounds on the area that we're interested in, the area between these 2 points. And those lower and upper bounds, those are given by those two perhaps rather horrible looking summations. So what do we have? The lower bound, we add up over all of the rectangles we're going to be looking at, starting from 0 up to the upper limit -1, the width of that rectangle base, the value of the function at the starting point, plus k multiplied by h. That's our lower bound. For the upper bound, we start summing from k equals 1, and we go all the way up to the maximum number of rectangles. So these are two different sums. And for the upper bound, we have the width of the rectangle base multiplied by the value of the function at this point. Now, what we want to look at, we saw that if we choose smaller rectangle bases, we get better approximations. We get this value becoming closer and closer to this value. So in other words, as h gets smaller, as the width of our rectangle base gets smaller, then these two estimates get closer together, but we cannot let the width of our rectangle base become 0, because then we're involved with a division by 0. So at this stage, we reintroduce limits. We've argued that the area we are interested in between these 2 points, that is the limit as we choose smaller and smaller rectangle bases of this summation here. The value of that rectangle base, the width, multiplied by the value of the function at this point here. And maybe that doesn't look very helpful. What if we knew that the function we are looking at, little f of x, was the first derivative of some function capital F of x? What if we knew that? So in other words, we take capital F of x, we form its first derivative, and the function we obtain is the function we started with, small f of x. How does that help? Well, in order to see how that helps, we have to go back and look at what does it actually mean for one function to be the first derivative of another function. What does that actually mean? Well, what it means is that our function, small f of x, is obtained by analysing this expression here. This is what we saw in our first principles analysis of what the derivative means. And so, having observed that, and having postulated the fact that the function we are looking at is the first derivative of another function, this tells us that our area expression is just this. We have the limit as the rectangle base approaches 0. We have the summation over all the different rectangles, and then we use in this point here the fact that the function we are analysing is a derivative, the first derivative of another function. So that's what's happening within the term we replace inside the summation. However, we don't need two limits. We've got a limit as h approaches 0 here. We've got a limit as h approaches 0 here. But we only need one of these. So we can just, in effect, forget about this and analyse how this behaves in terms of what is happening with the outer limit here. So we put everything together. What happens? The area we want turns out to reduce to this expression here. The limit as our rectangle base approaches 0 of this summation here. And this is our first principles, first derivative definition for the function big F of h, which corresponds to our function little f of h, which we are analysing. Now, I'm not going to go through the simplifying what happens with this. That's given in the textbook if anyone's really interested in looking at what happens. But what it turns out is that this expression simplifies to get this. The value of our function big F at the upper end of the measurement minus the value of our function big F at the lower end of the limit. So the area that we're interested, the area spanned by our function between the 2 points, this is just this term here. So big F at the upper point minus big F at the lower point, where this function large F, this has a property that when we differentiate it, when we form its first derivative, the outcome is our function small f of x. So I'm going to have to introduce a little bit more terminology, a little bit more notation here. So this function, with the property that when we differentiate it, we recover our starting function, this is called the antiderivative of f. So we have first derivative of big F of x is small f of x. The other way we refer to it is as the antiderivative function. Now, there's one complication we have with integral calculus, which is if a function has any antiderivative at all, then it has infinitely many. And the reason for that goes back to one of our basic differentiation rules. Suppose this function is an antiderivative of another function. Then it's the case if we add any constant value to the function, that's also an antiderivative. So obviously we have infinitely many constant values, we get infinitely many antiderivatives. So that's one problem. In differential calculus, we don't have that problem. If a function has a first derivative, that first derivative is unique. The notation we introduce is, I'm sure some of you may have seen this before, is what's called the integral sign. So we write the fact that a function is an antiderivative of another function. The way we write that is capital F of x is the integral sign of small f of x, and we write this dx in here. We have this other form that's used, and the reason is we distinguish cases where we have a specific area that we're interested in between two values from those where we're just interested in general functional behavior. So this is called an indefinite integral. This is called a definite integral. So here's an example. Let's go back to the case we started with. The function f of x is x squared between the values 6 and 14. Oh, but it's not too difficult to see that the function x cubed divided by 3, this is one antiderivative of the function x squared. If we differentiate this function, 3 times a third is 1, and we have 1 removed from the power, and so we recover x squared. So if we look at the area we are trying to calculate, that turns out to be, we evaluate the antiderivative function between 6 and 14. That gives us this expression here, which if we simplify it, turns out to be this quantity. As with first derivatives, there are a number of standard rules we can use for integrating basic functions. I'm not going to run through those rules. Those are given on this page of the textbook. One of the complications we have is there are many very simple functions which do not have a simply described a closed form antiderivative function. A number of those that arise in statistics, but even things which are superficially very simple, such as the square root of sine of x. So let me just summarize what we've seen in our review of calculus. In differential calculus, the principal importance is in optimization methods, and this is even with the complications we've seen with multivariable functions. Differential calculus is also important in deriving algorithms for finding roots of polynomials and in fact roots of general functions. For integral calculus, this deals with an important computational problem, that of measuring the area of a complicated surface. The techniques we develop in integral calculus can be extended to other area measurement problems. So things such as the volume of a three-dimensional object, the length of a line, and again these are discussed in the textbook. It also, and this is something we'll see in the next part of the module, has a very important specialized use in the area of algorithm analysis. And I'll be moving on to that in the next section of the module.